We will wait
So,
for 1 minute. 4 o'clock it is.
No.
So I think 21 people have joined. So maybe we can start.
I think we can, Aruna.
Yeah, fine. So welcome everybody. So we are happy to have Dr. Swara Ravindranath as a speaker for today's IA-50 commemorative lecture. So Dr. Swara Ravindranath received her PhD in astrophysics from the Indian Institute of Astrophysics, Bangalore. Her thesis was on star formation in starburst galaxies, which was entirely based on observations from the Venubapu Observatory in Kavalur. So she did her postdoctoral research at Carnegie Observatories in California and then at the Space Telescope Science Institute in Baltimore. Dr. Ravindranath joined the Inter-University Center for Astronomy and Astrophysics in Pune as an assistant professor and then became an associate professor. Thereafter, she moved back to Space Telescope Science Institute, where she is currently working as a scientist for the James Webb Space Telescope, JWST, which is set to launch in October 2021. She is also a member of the science investigation team for the Nancy Grace Roman Space Telescope and a member of the International Science Development Team for the 30-meter telescope. Her main research interest includes galaxy formation and evolution. She has been a collaborator on many deep survey observations using the Hubble Space Telescope and has used the high-resolution images to study the morphological evolution of galaxies through cosmic time. She also uses spectroscopic observations of star-forming galaxies to understand the physical conditions in the nebulae produced by hot, massive stars. Her current research is focused on identifying spectral diagnostics, which can be used to study the galaxies in the reionization epoch of the universe. So, with this brief introduction, on behalf of the IA-50 Organizing Committee, may I invite Dr. Swara Ravindranath to deliver her lecture on Deciphering the Nature of Ionizing Stars using Nebular Spectral Diagnostics. Swara?
Well, thank you, Aruna. I hope you can still hear me.
Yes.
Okay. So thanks very much for inviting me and giving me this opportunity to talk at this truly remarkable event, which marks 50 years of IA and its active astronomy research. It's always been and continues to be an institution that offers new state-of-the-art opportunities to young researchers and aspiring astronomers in India. And in this talk, I just want to spend the first few minutes going down the memory lane, just to share some of my memories from the days at IIA. And then I'll spend the rest of the talk telling you about some of the research that I've been doing in the last 5 years or so. So I really had the privilege of starting my astronomy career at IIA as a research student. I was working with Dr. Tushar Prabhu on the topic of star formation in starburst galaxies. And like Aruna mentioned, my thesis was entirely based on data taken from the Venubapu Observatory in Kavalur. And as I was preparing to give this talk, a lot of friendly faces, very inspiring conversations just came across my mind. And interestingly, I even found this little ID card of mine from IIA when I was a senior research fellow. And I just found that there were so many reasons why I just felt so thankful and privileged to be part of IIA. First of all, thanks to Dr. Prabhu, I learned most of my initial observing techniques and astronomy techniques from Prabhu. And I was fortunate enough that I could work with him, and he gave me so much freedom to work on topics of my choice. And he just let me grow on my own. really never kind of interfered too much, and he really stepped in to help only when I really needed the help. And I think that kind of freedom really helped to take advantage of the environment that was there at IIA. I'm very thankful to him, and also to many of the people with whom I've had so many interesting discussions. So I just thought I'll take a slide to just go down that memory lane and just kind of convey my gratitude to the Institute. So first of all, by the time I joined, I as a research student, the 2.3 meter Vanuatu telescope is already operating with CCD detectors, which were state of the art at the time, and also we were equipped with all kind of reduction software that was state of the art at that time. And also the 2.3 meter telescope was actually the largest optical telescope facility in Asia at the time. So, for a research student who's just joining the institute and, having that kind of facility was, you really felt privileged every time you walked into the 90-inch dome. And also now in retrospect, I don't have the time to go through all of this, but in retrospect, I see that IIA had leadership on so many fronts, especially as I grow and face different situations in life. I begin to realize how much of a leadership IIA had in many, many respects. So that's really been great. Another thing I'm really thankful for is, we had faculty members who had expertise both in observations and theory. And I know that experiences vary among people, but just to be very honest, from my opinion, I had really very good interactions with all the faculty members, and with most of them, I've had really good discussions, and I found them easy to talk to go and discuss things. And now, when I recall some of the conversations, I remember that everyone was so passionate about their research area. So even if you showed a little bit of eagerness to talk to them, they would give you all the time and tell you about their research. And there are so many things I learned, things that were not directly related to my research, but I just got motivated by talking to the faculty members, and so that was really helpful. And very early on in life, I realized, especially because I was so strong on the interstellar medium studies and stellar evolution studies, and my research was in galaxies. By talking to the faculty, very early on, I realized that you'll never learn about galaxies if you don't know about dust and gas and stars in your own galaxy. Um, Another thing I'm thankful for is the excellent library and staff. I just remember that we spent a lot of time in the library, and we had very competent and professional library staff who, if you went and asked them about a certain book or a research article, they would know about it. And back in those days, because we didn't have all these online, literature search, everything was, library was the big resource. And I remember there were times when, if you didn't find a research article or a book at the IIA library, the staff would actually get it for you from the Raman Research Institute or the Indian Institute of Science. And it didn't matter whether the request came from a faculty member or a student, they would just get it for you. So, really, thanks to them. Another thing I'm really thankful for is the innovative instrumentation group and engineers that were there at the Institute. I remember having really interesting conversations with members in the photonics lab. There were so many things that you could talk about, whether it be mirror polishing or the days of installation of VBT. You could even talk to them about active optics, adaptive optics, although those were not installed or working on any of our telescopes. That was a big thing back in the day, and they were knowledgeable enough to have a conversation about that. And also, I remember the electronics lab across from the computer center, where they were installing a mosaic CCD. Mosaic CCDs are common nowadays, but back in the day it was novel. And I remember that they had this really big DVAR in which they were filling the liquid nitrogen. And if I went to the lab, they would actually show me the big CCD window compared to the single CCD that I was using at 90-inch. They would show you this, through the window, big CCD window, you could actually see the CCD mosaics. And I remember having good conversations with the engineers there. It was mostly chit chat, but you learned a lot from the conversations with them. They used to talk to me about how difficult it is to actually develop controllers for Mosaic CCDs. Again, this was back in the time when this was very novel. So I learned a lot from them as well. And also, IIA was already an institution that had multiple observatory facilities. So it had stations in Kavalur, Kodaikanal, Gauribidanur, and also while I was doing my thesis, Hanle was also coming up. So you kind of really felt that you were in an institute which had a rich heritage of astronomical observing. And, that was again very motivating. So I really want to say that I had very enjoyable experience of scientific discussions with the faculty, the even the research students. I remember even the research students used to have a lot of discussions, and everybody was very passionate about whatever they were doing for their thesis. And I learned a lot about stellar astronomy, mostly through discussions, really, because that really was not directly my field of work. And all in all, I just want to say that I really had an environment where you can actually foster your ambitions and goals. So, what I really want to do on this occasion is say a big thank you to the Indian Institute of Astrophysics. I really feel, very thankful and privileged to have been a research student there. Now, I want to share a few photographs that I had taken while I was at IIA. The photograph that you see on the left is the Bangalore campus. It's not the most flattering view of IIA, but it's very dear to my heart because when I looked out of the hostel window, this was the view of IIA I would get every morning. So that view is very special to me. And here is another picture of IIA library. Again, I have very fond memories of the IIA library because although we all had offices, I think we spent a lot of time in the IIA library discussing things and, all those tables. I mean, I've sat at those tables and worked both day and night. And also those chairs, those lounge chairs where, we've had so many interesting discussions. So all really good memories. And then here are the two telescopes in Kavalur at the Vainu Observatory that I have actually worked on. I started most of my observations at the 1 meter telescope, but a lot of my thesis really was based on the data that was taken from the 2.3 meter Vainu telescope. And there again, I want to really thank all the night staff for, you know, really being very patient with a young research student who wants to open up the dome every time she sees one star in Orion. They knew better. They knew about the sky conditions much better than I did. And also thanks to all the engineering staff, of course, the weather conditions were not always perfect, so there was a lot of time for discussions, and they kept sharing information about, generally about the optics, about instruments, detectors, and sometimes just fun stories about installation of VBT. So really, I mean, very interesting times. And what I really want to say is, from all these discussions, it just gives you various perspectives, and you just develop as an astronomer. You have a better feel for the kind of career that you're getting into. So, I mean, all of this really prepared me for the career. So, thanks to all of you. And here is finally the actual telescope that I worked on for most of my. This was really the workhorse telescope for my thesis. So my thesis was titled "Star Formation in Starburst Galaxies," and it was entirely based on the imaging and spectroscopy from this telescope. There was, I mean, when you work with a telescope for so long, you begin to get a feeling that it's your telescope. So for me, that was, VBT was really like my telescope while I was there. And just because I'm closing the slides on my walk down the memory lane, I really wanted to kind of show the transformation in various things that had gone through while I was observing at Kavalur. So I remember that the first few years I had actually gone to the observatory with a magnetic data tape, and by the end of my thesis, we had already moved on to exabyte. Similarly, when I started, we had VAX VMS computers, and was not particularly friendly for me. Luckily, the the Spark station came by the end of my, while I was there. So that was the computer that I used for most of my time. And I also had the privilege of actually doing manual guiding at the 40-inch telescope. And I was there when they switched finally to auto guiding. And I was one of the, PhD students who was there and observing. So I was like the test particle to see if the auto guiding was working fine. Yeah, so all of this really prepared me, and I'm just feeling very thankful. So with that, let me actually go into the science topics. So let's start with my thesis first. So my thesis was essentially on star formation in nearby starburst galaxies. And the galaxies that I had chosen to study were infrared bright galaxies. So these are galaxies which have a lot of active star formation going on in them. And the massive stars formed in the recent starbursts essentially heat up the dust, and the dust then re-radiates in the infrared, which is why these are very, bright in the red filters. And most of my imaging studies were based on broadband imaging in the BVRI filters, and also I did, some narrowband imaging in the H-alpha emission line, which is a recombination line, which is quite bright and very useful for studying star-forming regions. So just to give you an example of the kind of analysis that I was doing with this data, so with the broadband images, I basically used them to look at the dust features and understand the dust distribution in the galaxies. With the H alpha images, essentially, you would remove the continuum, then you have the pure emission line image, and I use that basically to study the properties of H2 regions, looking at things like the H2 region luminosity function, which was known to vary with Hubble type. So quantifying that was one work that I did, and we also looked at other properties like the H2 region size function, and also some of the scaling relations that you expect from radiation-dominated H2 regions. And H alpha line is a very good tracer of massive stars and emission from massive stars. So we use that also to quantify the star formation rates, and also get a handle on the number of ionizing photons and massive stars in these star forming regions. I particularly want to highlight the work that I did on this galaxy, NGC 972, which was a very interesting galaxy. And surprisingly, there wasn't much work done on this galaxy. It caught my attention because, to me, in some of the images, it actually looked like M82, the prototype starburst galaxy. But the thing about this galaxy is it's very dusty. And when you look at the H alpha image, you can see how much hidden star formation there is beneath the dust. And so we essentially looked at the H2 regions, the H2 region properties, and so on. But the thing is, I mean, we really didn't have a capability for taking spectroscopy at the time. And I remember I actually reached out to Louis Ho at Carnegie Observatories, and he had the spectra of the H2 region in the nucleus, or the H2 nuclei, nucleus of this galaxy. It was a spectroscopy taken from the 5-meter Hale telescope. So he shared that data with me, and then I combined all of this data, and we had a paper that was published in 1998, just on this galaxy. And one of the things that we found from the emission line ratios is that the emission lines are not simply powered by photoionization alone. They also do have a contribution from shocks. So I was already really excited and fascinated about using Spectra, and was a little sad that we didn't have a spectrograph. But luckily, I was really fortunate that the OMR spectrograph was installed at VBT during the last 2 years of my PhD thesis. So thanks to Dr. Prabhu, thanks to Dr. Anupama, and thanks to Dr. Surendranath. Uh, and as you can see here, it was a new state-of-the-art, efficient, medium-resolution CCD spectrograph, which was put in operation during the observing season of 1997. But again, like I said, so it just came right in time for me. So I was really fortunate to use that in the last 2 years. So it was really nice that I could now get emission line spectra of the galaxies. So you could get all these diagnostic lines, like the H beta line, the O3 line, H alpha, N2, sulfur 2 lines, and the sulfur 2 doublets. So essentially now you could derive various properties of the ionizing regions, like the star formation rate from H alpha. You could use the O3 lines to get the metallicity. You could get information about the electron density from the sulfur doublet. And that really just told you a lot about the kind of massive stars that are ionizing these nuclei, or star forming regions. And you can actually look for the presence of low luminosity AGNs like liners, or if there is any contribution from shocks. And also the spectrograph was quite sensitive all the way to about, close to about 1 micron. So essentially you got all those calcium triplet features that come in the zero point 0.8 to zero point 0.9 micron region. And the calcium triplets are very strong when there are red supergiants. So you could use those spectral features to actually understand the stellar population and their metallicities and stellar ages. So I really feel fortunate. I could kind of, at the end of my thesis, I was kind of really prepared with both imaging and with enough training in spectroscopy to then pursue my future career. So I'm going to spend the rest of the time just essentially talking to you about more of the recent research work that I've been doing. So my interest, from the time of my postdoctoral studies, my interest had already moved to understanding more about galaxy formation and evolution, essentially studying how galaxies have evolved across cosmic time. So I've been working a lot with deep surveys with Hubble Space Telescope. Uh, so the first deep field that I was familiar with when I was a grad student, the Hubble Deep Field was just being the observations were just being carried out. The new results were just beginning to come in. But I had the good fortune to actually work with the GOODS collaboration, the Great Observatories Origins Deep Survey. Now that was a fairly deep survey that took you all the way back, to Redshift 6 or so, which is essentially like the initial, 950 million years of the universe. So it's less than a gigayear. And then later, while I was a postdoc, there was also the Hubble Ultra Deep Field that was taken, which essentially pushed the frontiers, a little beyond that, and you're actually looking at 900 million years or so of the universe, the initial 900 million years. So I have then also been fortunate to work with, another a wedding cake like deep survey where there were some fields that were observed, which is a candles collaboration essentially. So it was an HST survey of 5 fields in the near infrared imaging, essentially kind of really pushing the frontier of what redshifts you can observe, because you're essentially looking at galaxies whose light have been redshifted to the optical light has been redshifted to the near infrared. And this survey essentially had, 2 parts to it. One is the candles wide, where about 800 square arc minutes of the sky was surveyed down to a magnitude of about 26.8 magnitudes, AB magnitudes, and there was a deep component to it, which looked at about 125 square arc minutes down to about 28 AB magnitude. So using these, what is nice about this data is that when you look at a field like this, if you look at the figure on the left, um, you know almost everything that you see here is galaxies except for 1 or 2, maybe few stars. And when you actually zoom into the individual regions like the one that I've done here, and you can see the zoomed image on the right, you can actually see how much detail is visible for these high redshift galaxies, and also how deep you probe. Some of these very red galaxies that you see there are high redshift galaxies where you're only looking at them, in their first 2 billion years after the Big Bang. So this is the kind of data you can actually use to study the evolution of galaxies with cosmic time. And my initial studies were mostly based on, galaxy profile fitting and size determination, essentially trying to understand how the morphologies of galaxies have transformed. Because when you look in the cosmic past, what you see is that most of the galaxies had a very clumpy morphology or a very irregular morphology. They often show signs of minor mergers. And also, the other thing you notice is that as you see this figure on the right hand side in the bottom, if you look at the size evolution, you can actually see that the star forming disks were much smaller and had much smaller scale lengths at high redshift. And this is in spite of correcting for whatever the resolution is. It's not really a PSF effect. Even after you correct for that, you can actually see that galaxies do have a much smaller size. Now, the one thing to remember is that these are sizes measured in the UV. So one of the things that the James Webb Space Telescope will be doing is looking at the optical images of these galaxies, the rest frame optical. So you will be able to really say whether the compact sizes that you measured were in any way biased by the wavelength. And the figure there on the right-hand side top shows you essentially a beautiful figure that has been put together by Casey Papovich by using images from the deep surveys, essentially picking up candidates at different redshifts, which could have been the progenitors of something like the Milky Way galaxy. And this is just really a just a representation to show how these galaxies that had small morphology, small sizes, how they would have kind of evolved in the color redshift space to finally form something like the Milky Way galaxy by the time you reach to lower redshifts. So you're starting from roughly 2.8 redshift, and then you try to see the candidates that could have represented the progenitors of Milky Way all the way to the present day, which is shown in the top panel. And Another area which I focused on was really looking at the morphologies of Lyman break galaxies, which are star-forming galaxies at redshift 3. And one of the things that I noticed was these galaxies actually are very clumpy, and there is something interesting about the clumps in the sense that they're kind of unique to what you see at high redshifts. These clumps are kiloparsec sized, and they have masses of 10 to the 7 to 10 to the 8 solar masses. Now contrast this with star-forming clusters that you see in nearby galaxies, which are usually only about, even superstar clusters are often less than 100 parsecs in size, and the masses are less than 1 million solar masses. So these are really a different kind of beasts altogether. And the way you understand the formation of these clumps is that, I mean, the disks that you find, the star-forming disks that you find at high redshift, they're very gas-rich. So if you even just think about it just from the Toomre instability criterion, we know that there is this little equation that tells you about the Toomre instability criterion for a gas-rich disk. So essentially, when you have a gas disk, you have self-gravity, which is the one that is trying to kind of collapse or fragment the clouds. And there is the pressure and the rotation, which are essentially kind of giving you the support against gravity. So as long as they're balanced, you are in a stable configuration. But if there are regions where the Q parameter becomes less than 1, then, of course, self-gravity begins to take over the opposing forces, and then you have the collapse and fragmentation of the gas clouds. Now, if you look at some of the kinematic data that is available for redshift 2 and 3 galaxies, which is what is shown in the bottom, that colorful picture there. So those are essentially data from the Symphony IFU on the VLT. And this is work done by Gensel et al. In 2011. They looked at some of these clumpy galaxies and got the kinematics and found that these systems were very turbulent in the sense that their rotation velocity was comparable to the velocity dispersion. So overall, I mean, their Q parameters were high and they were just dominated by turbulence and violent instability. So the places where you actually form the massive clumps are, so you can see an H alpha image here, which essentially shows you the location of the clumps. And in the velocity maps, the regions where you've formed these clumps are localized regions where the Q parameter becomes less than 0.5. So in the color code here, you can actually see when it gets more bluer and then to purple, that's really the low Q value locations. And that's really where you actually form these very massive clumps. So it's really like a local instability that sets in. And theoretically, again, there've been a lot of work that's done on these gas-rich disks to understand the formation and evolution of the clumps, especially because these are such massive clumps and with high surface density. So they must have a profound implication on how galaxy assembles and how the bulge is formed. So what the hydrodynamical simulations show is that it all is really dependent on the ability of these gas clumps to migrate inward. So these mass clumps, which are really massive and have very dense, high density, they essentially move inward by dynamical friction. And all along the way, they can be subject to a lot of energetic feedback from star formation, which could be supernova or even winds. So it's really a question of whether the star forming clumps can actually survive and then, migrate all the way to the center of the bulge. Or there could also be contribution to the bulge formation from clumps or, small merging star clusters, which can originate from external to the disk, and they are the ones which are called ex-situ clumps. So one of the research topics that's very active nowadays is to understand what is the role of these massive clumps in galaxy assembly and bulge formation. Like, how much is the contribution of ex situ clumps, and how many of the in situ clumps, are the ones that are actually formed within the disk, which are called in situ clumps, how many of them are able to survive, and which ones contributed to form the bulge? I mean, was it a major contribution from the external clumps, or was it the in situ clumps? Another interesting thing to notice also is that a lot of these clumpy galaxies have been observed also in the Hubble frontier fields. So Hubble frontier fields are really deep field surveys of galaxy cluster fields. So when you have deep images of the cluster fields, the advantage is, in addition to the power of your telescope itself, you're also taking advantage of the natural magnification that is offered by gravitational lensing, and you get these magnified, amplified images of background galaxies. So the cluster may be at a redshift of zero point 0.4 or something, but you get distant galaxies at redshift 6, redshift 4, redshift 5 that are actually lensed, and you can see them in much better detail. And there are two images that I'm showing here on the left-hand side, which are galaxies at around redshift 3 to 4, and you can actually see how those images are magnified, and everything that you see there as marked as 20 in the first figure is essentially one galaxy, and those different points that are marked as 20.2, 20.8, and so on, those are the individual clumps all belonging to that same galaxy. And same way, in the bottom plot, there is another galaxy just designated as 106 here, and you can see there are at least 6 clumps that are actually seen at the HSD resolution. And with Muse, there is also Muse data available on this field. So, it has been possible to actually study these both in the emission lines as well as in the continuum. And from the continuum, one of the things you can actually measure is also the size and the magnitude. And I particularly want you to pay attention to these clumps, the ones that are here. So 1C, which is down here, you can see that the half width at half maximum of uh, uh, this clump, it's only about 10 parsecs. So that is almost getting down to the size of individual star clusters. And then there is another one here again, this yellow point here, which is again, just few tens of parsecs, but these are at redshift 6.6. So this is like, almost seeing the first protoglobular clusters, which are being formed, when the universe is only less than a billion years old. And these are the areas where we think that the next generation of telescopes are going to make a huge impact. In particular, the James Webb Space Telescope is going to observe a lot of these. And there's also going to be the Giant Magellan Telescope that's coming up, and then there is the 30-meter telescope. And if you look at the spatial resolutions that these telescopes are able to offer, James Webb would offer you, something like about 14 milliarc seconds, and then the Giant Magellan and the 30-meter telescope will get you down to something like 7 milliarc seconds, 4 milliarc seconds. Those are the kind of spatial resolutions that you need to really confirm the properties of star clusters and so on. And they also are equipped with spectrographs that have high spectral resolution extending all the way to the near infrared. So you can essentially start getting kinematics of these high redshift clusters and really study some structures at the earliest epochs of galaxy assembly. And there is a JWST ERS program, which is the Early Release Science program, called Cosmic Evolution Early Release Science Survey, which is again the same team that worked on candles. So I'm part of this program, and I'm really looking forward to kind of following up this, studies of star clusters with that data. So with that, I want to move on to the next topic, which is actually the thing that I'm currently working on very actively, which is to use extreme emission line galaxies to study reionization. So here is just a quick overview of the cosmic timeline. So we know that the Big Bang, I mean, the universe was created in a Big Bang, and the initial few seconds was essentially just a whole hot soup of particles, basically just protons, neutrons, and a time of very high opacity when the radiation really could not escape. But then, as the universe expanded and cooled, and the initial ionized hydrogen and helium were formed from the protons and neutrons, and then they started capturing the electrons and actually forming neutral hydrogen and helium, predominantly neutral hydrogen, and that is the epoch when. Uh, which is called the recombination era, and that is the time when light can actually escape because it's no longer optically thick, and it can actually filter through without being scattered off from the free electrons. And so after recombination, you enter this period which is known as the dark ages. So that extends all the way till the universe is about 300 million years old, because you really don't have any source of light or any source of ionization at that point. But we believe that the first stars and first galaxies formed after about 300 million years. Again, the actual epoch of the formation of first stars is still debated. We still don't know. We hope that the new observations will take us there. But that's roughly the kind of time frame. Redshift of around 20 to 15 is where we think that the first galaxies would have formed. Now, once these galaxies are formed, then you have a source of light, and you also have a source that can actually ionize the neutral hydrogen medium around it. And then it's kind of a percolation effect, because there is more and more high density regions that are forming more galaxies and more stars, and then you have more ionizing radiation, which can then ionize most of the neutral intergalactic hydrogen gas. And then finally, by redshift 6, you get into a time when the universe is almost fully ionized. However, there are a lot of things so that epoch, which we call the reionization epoch between redshift 15 and redshift 6, is a time where we really don't know a lot of information. I mean, we have a story, but we don't have enough evidence to back the story. So some of the questions that we want to ask are: what are the sources that reionized the universe? Was it really just star formation? Is it all pure star formation, or are there other sources like mini quasars or something, something that are AGN like? Because there must have been some seeds of black holes that were formed. There must be seed black holes that were also formed at around that time, and they definitely must have an impact. So, was it AGNs or star formation? And so we really need to characterize the nature of these ionizers. And the other big question is, it's not enough to just have an ionizing source, because you're surrounded by hydrogen, a neutral hydrogen, not only in the intergalactic medium, but also within these galaxies that host the ionizing sources. So it's a question of how much of the radiation can actually escape the galaxies and be available for ionizing the intergalactic medium. Now, we can actually draw some inference from the kind of active star formation activity we find even in the local universe. So, if you look at the star forming region NGC 3603 in our galaxy, or if you look at the 30 Doradus region, which is a very, very active star forming region in the LMC, our neighbor, you can actually see in regions where there are these hundreds and thousands of massive stars being formed, the effect on the immediate environment is very significant. Not only can they ionize large volumes of gas around them, they can also actually have powerful winds and feedback that can actually blow holes in the medium that surrounds them. And that is one way in which your ionizing continuum radiation can actually escape into the intergalactic medium. So the current picture, if you zoom into the epoch of reionization, this is roughly a picture of a cartoon picture, really, of what we think must have happened. So you would have these pockets of very intense radiation that's coming from the first stars, and these stars and first galaxies and first stars, particularly first galaxies, because they would have larger number of massive stars. And the thing to remember is that these are stars that are being formed with very low metallicity, and so they're likely to have a very hard ionizing spectrum, and they're going to really be able to ionize large volumes around them, and then this kind of percolates, and then the bubbles begin to merge, and then finally by the end of the reionization epoch, you kind of have all these bubbles, ionized bubbles that have merged, and we enter into that phase of complete ionization. So if you wanted to study this, and if you really wanted to probe the sources that are causing the ionization, one easy indicator would have been Lyman alpha emission, because this would be the brightest UV line in any normal star-forming galaxy, and that would be your first way of identifying the ionizing sources. However, the problem is, like we just mentioned, the intergalactic medium is neutral, and Lyman alpha is a resonantly scattered line, and there's so much scattering, and you would hardly detect these lines. And it's already evident that by the time you go to redshift 7, so here is a figure that essentially, I think I took it from Tilby et al. 2014. Pay attention particularly to the raw data, which is the orange points that you see here. You can see that when you look at the bright Lyman alpha emitters, once you reach about redshift 7, there is this big drop in the number of Lyman alpha emitters. And even if you think it's a completeness effect, even if you look at the faint sample and do completeness correction and so on, you can still see that there is this big drastic drop beyond redshift of 6.5 or so, which essentially is because of the high IgM opacity to Lyman alpha transmission. And you only, even if you only have about 10 to 20% neutral hydrogen, that can lead to Lyman alpha non-detections. So our real best bet then to actually identify high redshift galaxies is just by looking at the continuum emission, which can be captured in these kind of very deep images. The image that I'm showing you here is essentially the Hubble Extreme Deep Field, which is the deepest image of the universe that we have currently with the Hubble Space Telescope. And it has been taken by combining all the HST ACS, which is the advanced camera for surveys and operates in the optical. And there's also the data from the Wide Field Camera 3, which operates in the near infrared. And this is all on the same region, which is called the Hubble Ultra Deep Field. And all of these were combined to form the deepest image of the universe. And it's a small region. It's a very pencil beam deep survey, covering only about 4.7 square arc minutes area. But it's reaching something like 29 to 30 AB magnitudes. And that is kind of almost getting to the regime where JWST will be working at its best. And that means in absolute units, you're almost looking at galaxies with absolute magnitudes of minus 17. So that would be like looking at dwarf galaxies almost in the local universe. So that's the kind of magnitudes we are now probing at redshift 7, and this will really be the key science area for JWST. So once you have images like that, you can use some of the spectral features to pick out galaxies at different redshifts. And one of the most robust determinations have always been by using the Lyman continuum break. So when you look at the spectral energy distribution of star-forming galaxies, particularly in flux density units versus wavelength, you can actually see that the spectrum is fairly flat in the ultraviolet. This is the rest-frame ultraviolet that you're seeing here, essentially redshifted to these wavelengths. And by the time you reach, so all of the ionizing photons that come with energies greater than 13.6 eV, which is the ionization potential of hydrogen, all of the high energy photons are essentially being absorbed by the neutral hydrogen, both in the galaxy and the immediate IgM. So that leads to this very sharp break in the spectrum, which is what is known as the Lyman break. And this feature gets redshifted to observable optical and near infrared wavelength at redshift 4 and beyond. So by the time you reach redshift 4, you can see that in the ACS filters, which are the blue filters, you don't really sample any of the light at 4,000 angstroms, but the light the Lyman break comes in at about 6,000 angstrom, and you start sampling the ultraviolet light in the 6,000 angstrom filter, and then redward. And you're beginning to get all of the UV continuum longward of that. By the time you get to redshift 6, you have nothing in the optical filters. It's pretty much all of the light is beginning to come only at around 8,000 angstroms. And that's what you see here. It begins to register in the F850 filter, which is where you sample the 8,000 angstrom light. And then redward of that, you get all of the rest UV continuum. And by the time you reach redshift 10, with what we have on HST, you can see that you can only see the galaxy in that last filter, in the H-band filter, because all of the UV continuum has shifted beyond that. And you can use two-color diagrams like the ones that I show here to pick out these high redshift galaxies, because essentially you're sampling the spectral energy distribution on either side of the Lyman break, and that essentially picks out galaxies that have these very extreme colors, and that is a way in which you can actually identify samples at different redshifts. Now, once you have galaxies at different samples of galaxies at different redshifts, then you can essentially form what is called the UV luminosity function, which is basically telling you how many galaxies of different luminosity you have, or in other words, you can actually convert that into a star formation rate, and that will essentially help you understand how the cosmic star formation rate density has evolved with time, which is the figure that is shown down here. Now, the thing to remember is that we have a fairly good estimate of the luminosity function at redshift 7, but by the time you reach redshift 8 and 10, we have very little handle on very little tight constraints on the UV luminosity. So the kind of things we want to constrain are the faint and slope, and also get the actual complete samples of galaxies at redshifts greater than 8. And when you look at the cosmic star formation rate density, the way we know now is that it peaks at a redshift of about 2, okay? And then it kind of has this rapid decline. It kind of slowly declines to higher redshifts. Now, the thing to notice is after redshift of 7, you can actually see this purple line which goes through the observed points, and they seem to be falling very rapidly. And we don't really know whether this rapid decline has anything to do with our bias of observations, or whether this is actually real. And again, this is one of the things that we hope that JWST will really probe and tell us whether this rapid decline that we see is true or not. Because if you expected the trend that you see at redshift 4 to show that monotonic decline, then you don't really expect this kind of a sharp break at redshift 7. So this is the real gap that we hope that JWST will close. And this is really important because you really need a large number of star-forming galaxies to reionize the universe. And if your numbers are going to drop like this, then the only way you can then get enough ionizing photons is if the escape fractions are very high. So there is this interplay between the number of ionizing photons or number of massive stars that you have versus the escape fraction. So if your number of luminous galaxies are going to decrease like that, then you really need a very high escape fraction to kind of account for the ionizing budget that you need for reionization of the universe. So on that topic, we're still kind of debating whether AGNs or star-forming galaxies are responsible for reionization. AGNs were initially ruled out because when you looked at the population of bright AGNs, they showed this rapid decline after a redshift 2 or so. So they were never considered as very good candidates. However, there have been recent studies which show that when you have deeper surveys of AGNs, and you can actually reach low luminosity AGNs, their number seems to be, kind of compatible with what you need for reionization, if this trend will hold up to high redshifts. Okay, so there is improvement over what we knew earlier, but the question is whether this trend actually goes on into the reionization epoch or not. And as far as star-forming galaxies go, with all the information that we have as of now, we can account for about 30% of the photons that are needed for reionization, with reasonable assumptions of, the escape fraction. Again, it all depends also on your assumed escape fraction, right? If you have higher escape fraction, then you need lower number of star-forming galaxies. So under reasonable assumptions, we are able to account for about 30% of the needed photons. And we're hoping that JWST will be able to account for almost 60%, will reveal some of the star-forming galaxies down to, about a UV magnitude of -15, and that should account for about 60% of the ionizing flux that is needed for reionizing the universe. And there will still be very faint galaxies beyond that. If there is, light sources that are about -15 to -14, JWST probably won't, may or may not. We don't know the capabilities yet to that detail, but this regime would really require a larger telescope, like a 12-meter or a 14-meter space telescope. So since we talked about this question of whether AGNs are star-forming galaxies, how do we address that question? So the tool that we have in hand, from very long ago, since the 1980s, has been what is called the BPT diagram, which can actually use the line ratios of high ionization lines versus low ionization lines to actually make plots like these and identify the regions occupied by star-forming galaxies and AGNs. So if you have diagnostic figures like this, where you plot the O3 line ratio versus H beta against the N2 by H alpha, you can see that there are these regions that are nicely demarcated, which is occupied by star-forming galaxies here, and the AGNs are on the side. So you have the active galactic nuclei here, and the low luminosity objects, which are kind of transition between star formation and the real strong AGNs, and they fall somewhere here, but these are again black hole powered. So those are all, so the figure that I showed you earlier was essentially from the SDSS. That was the figure from Kaufman et al. 2003. So this is the BPT diagram that you get for the SDSS galaxies. Now, if you're trying to do something similar for galaxies at redshift 2 and 3, the first thing that jumps out is that, even the normal star-forming galaxies, they follow this trend, but then at a much higher ionization. You can see that the high ionization lines are much stronger. And they're almost beginning to kind of, merge into this region of the AGNs. And what this is essentially telling you is that star-forming galaxies at higher redshift seem to be having a harder ionizing spectrum. So they have more stronger high ionization lines. And one of the challenges that we have is when you go beyond a redshift of 2 to 3, all of these familiar rest frame optical emission lines now begin to shift, to higher and to longer and longer wavelengths and are not easily accessible. So even with JWST, most of the spectroscopy that JWST will do will be in the near infrared. And you can see that by the time you go to a redshift of about 6.6, H alpha is already at 5 micron. So it's already beginning to move into the mid infrared. We do have a mid-infrared instrument on JWST, but most of the workhorse spectroscopy will be done in the near infrared. So the optical line diagnostics are now getting redshifted beyond the near infrared at redshifts greater than 6. So we have to then rely on mostly the UV emission lines. So my research in the recent years is mainly focused on the UV spectroscopy. So let's see what we know about the UV lines from high redshift galaxies. So it's really difficult to get spectroscopy of galaxies that are at redshifts greater than 6. And the only way you can actually get spectroscopy is if you have candidates that are that are strongly lensed by galaxy clusters. And spectroscopy of these lensed galaxies show that they have, you do actually see the Lyman alpha emission, but you can see that the Lyman alpha emission is very weak in these galaxies because the IgM opacity is high, and the transmission for Lyman alpha is really, really small. But what you notice is that there are other very high ionization lines like carbon 3, which is the forbidden carbon 3 doublet, and also the carbon 4 and forbidden oxygen line at 1666. These lines begin to become very strong. And these are all data that were taken from the ground, and we hope that this is exactly where JWST is going to perform at its best, because it's going to have higher sensitivity, and also you don't have this issue of atmospheric night sky lines, which become very prominent in the near infrared. So these are just the rest wavelengths that I'm showing here, but these lines are essentially shifted to the near infrared. So Okay, so we know that we see these very strong UV lines. So redshift 6 is really difficult to get. But the nice thing is that for redshift 2 and 3, you can actually get the UV rest wavelengths even from the ground. And there have been a lot of studies that are done on Lyman break galaxies at redshift 2 and 3 at very low metallicities. And so when you look at individual galaxies, you really have to form the composite spectra to really get very high signal to noise. Whereas for lensed galaxies are the only cases where even for the individual galaxies, you can actually begin to kind of, get these features with high signal to noise. And one of the things that you notice that is that Lyman alpha is very strong for the lower redshift galaxies because there is no issue with the IgM opacity. But the next strongest feature that you see is the carbon 3 feature, and that is also seen at in these lensed galaxies. And the other UV lines that you see are oxygen 1666 and sometimes also helium. And helium is very interesting because you can have both nebula contribution as well as you can have a stellar contribution, which would indicate the presence of Wolf-Rayet stars. Now, one thing that you notice when you look at the C3 emitters at redshift 2 is that they also show very strong O3 5007 emission lines in the optical. And these lines, the O3 lines, have very high equivalent widths, almost 1,500 to 1,000 angstrom, which means even in the broadband, they tend to, even if you just did broadband photometry, you have these colors that, or the broadband photometry gets really very extreme colors because of the contribution from very strong line emission in the broadbands. And photoionization models show that these galaxies have very low metallicity, they have very high ionization parameters, and they have very, very young ages. So my research has then focused on, in order to understand these better, I decided to actually look at local analogues, which are the green pea galaxies, which again are galaxies with very high equivalent widths in their O3 emission. So these look like the best analogues we could actually study in much more detail in the low redshift universe or locally. And green pea galaxies are extreme in many ways in that they have very high O3 equivalent widths, they have very high specific star formation rates, they're very low mass galaxies, they have low metallicities, they have very high UV luminosity, and all of these properties are comparable to the properties of star forming galaxies at high redshift. And also from recent studies, we know that green pea galaxies are also good candidates for escape of Lyman alpha and Lyman continuum, and they're almost always seen as Lyman alpha emitters in the local universe. And one of the things that I found from my study is that among the green pea galaxies, there was a high fraction of C3 emitters. Now, this is an important result because until then, most of the studies that were done on star-forming galaxies at solar metallicities did not actually show the C3 emission. So it is very special that C3 emission really begins to show up only when you go down to about 1/3 solar metallicity or even lower. And then I kind of, along with Anne J. Scott, who was a postdoc at the time, I actually tried to understand what are the kind of input spectral energy distributions that you would need in order to produce the carbon 3 line, because this was going to be the main line that we would be using for redshift identification, as well as for understanding the nature of the sources that were responsible for reionization. So we actually looked at various input spectral energy distribution models, and the one thing that we found was that all of these input spectra at very young ages, like at around 1 million years, the different spectral, templates, be it from the, Padova tracks or from the Geneva models or the BPAS models, which include the binary stellar population evolution, all of them kind of agree for the very young ages. But as the star cluster gets older, you can see that the UV ionizing UV really begins to drop very sharply for all the other models. And it's only in the binary stellar population models that you're able to continue to have this. That's the one that's shown here in solid line, and you can see that that's the only model where you continue to get a nice ionizing flux even at older ages. And the Padova tracks actually briefly show you an enhancement at 4 million years, which is essentially because of the contribution of Wolf-Rayet stars. And we looked at the kind of, C3 equivalent widths, the predictions that can come from these photoionization models. And what we realized is that whether you use the Padova models, which are essentially non-rotating single stars with AGB, you know, influence included, or whether you looked at the Geneva models, which are again single stars rotating and including mass loss rates, the thing that you notice is that you can get very high equivalent widths of carbon-3, like around 14, only at the very young ages at extremely low metallicity. But at most of the observed metallicities of the galaxies, you cannot really get very high equivalent widths. And when you look at high redshift galaxies, their C3 equivalent widths are very often found to be more than, 10 angstroms, reaching 15 to 20 angstroms. And one of the things that we found in this study, by looking at the by looking at the photoionization models, was that only the binary stellar population models are able to provide you, high C3 equivalent widths at reasonable metallicities that are observed for the green pea galaxies, and also you can get high equivalent widths for a longer, stellar age or for a longer time scale. So they continue to have, like 15 or 10 all the way up to about 6 million years, which is the kind of ages that we derive for the stellar population. And again, just to show you the metallicity dependence of carbon-3, you can see that, so it's only when you go to about, 1/3 solar that you actually even begin to measure carbon-3. And if you really need to have high C3 equivalent widths above 3 angstrom, then you really have to be at very low metallicity, less than 1/5 solar metallicities. And here is another figure that's from Centena et al., which actually shows you how these emission lines show up at lower metallicity. And when you get down to about, like about 1/5 solar, you also begin to see carbon-4 and helium-2 in emission. So again, this has also been seen for the blue compact dwarf galaxies. This is again just a figure taken from Berg et al. 2019. And these galaxies are actually getting down to about 1/10 solar. And by the time you get to 1/10 solar, you can actually see these resonant lines of carbon-4. You can begin to see the helium emission. So really a lot of very interesting rich physics. And I have an HST proposal, which the observations haven't started yet, but that HST proposal essentially is going to target very high ionization sources, which have O3 by O2 ratios greater than 20, and we are hoping that they will have spectra like this. So essentially what happens is when you have very low metallicity, this is a figure which essentially shows you what is the kind of energy spectrum that you have. So the red line that you see here is, twice solar metallicity. And then there is the solar metallicity. And as you go to the blue line that you see here, it's essentially showing you the lowest metallicity, which is 0.01 solar. And what you notice is that, you begin to get more and more high energy photons in these low metallicity. The flux in the high energy photons is much higher in these low metallicity models. And you can see these are the kind of energies that you need in order to get the carbon-4 lines, right? I mean, you need like 47 electron volts or so. And you can see how, these low metallicity spectra have much more energetic photons to actually produce those strong lines. Or you can get the same from AGNs, because AGNs, of course, have a power law slope. So they are also very rich in the kind of high energy photons that you need to get. And here again is another plot from Felter et al., which shows you the how the different spectral energy distributions contribute to different emission lines. And this big swath of gray that you see here, this is essentially all of the AGN models. So you can see that the AGN models continue to give you very high energy photons, 60, 80, and so on. So if you're finding lines like N5 or, neon 4 and so on, then you know that you need the high energy photons coming from AGNs. But for most of the kind of lines that I have been talking about, be it helium or carbon or O3, you can see that you can either have very low metallicity stellar population shown here by the blue lines, which can give you that, and so that's essentially what this figure is showing you. Like higher metallicity, you begin to kind of lose the very high energy photons. So essentially, now that we have this information, we can go ahead and go back to that question of whether it is star formation or AGNs that contributed to reionization. But if we have to use this information that we have, we first need to, we don't have the optical spectral diagnostics, so we have to calibrate the UV spectral diagnostics. And this is what we are actually trying to do with a program called CLASSY, which is an HST program that I'm part of. And we're essentially using all of the UV spectra in HST, observed with HST, to kind of create a unique database to calibrate the UV diagnostics. So that's an HST legacy program. So now, similar to what we have for the BPT diagram, which is the common tool that we have used so far to understand AGNs and star-forming galaxies, now we have a similar diagnostic diagram using the UV lines. So if you use a UV diagnostic diagram that has C3 over helium line ratio versus the carbon-4 versus helium ratio, you can essentially separate out the ionization coming from star-forming galaxies versus the ionization that comes from AGNs, and it kind of neatly separates out the star-forming galaxies and AGNs. And also from J. Scott and Ravindranath, we also looked at the contribution of shocks. So what we found is that there is this kind of a region that is occupied by pure photoionization, and as there is more contribution from shock ionization, you begin to get this kind of a separate region that's populated in this diagnostic. So these are the two UV spectral diagnostic diagrams that we are hoping to calibrate at low redshifts so that we can use that information and apply these diagnostics to high redshift. And also in that paper, in the J. Scott and Ravindranath paper, we also went ahead and looked at what are the diagnostics that can tell us about the conditions that will allow the escape of Lyman continuum from the star-forming galaxies. Like I said, we are not going to see the Lyman alpha, right? So the only hope that we have is to use the optical lines and to use C3 lines. So we were trying to see, by looking at these rest frame optical UV spectra, would it be possible to get some information about the escape fraction? So the thing to remember is that by the time we look at something like the green pea galaxies, or by the time we look at very high redshift galaxies, we're beginning to get into a situation where you could have a radiation dominated H2 region, which would be like this, where you have the star cluster surrounded by the ionized region. There is still a lot of neutral gas, but the feedback from the star forming region is able to blow holes into the gas and form something like a picket fence geometry through which both the continuum and the ionizing continuum can actually escape. Or you can have pockets which are density bounded nebula, where you essentially have ionized all of the region that is available in the immediate vicinity, and then you can have the continuum radiation. This begins to free stream. And the thing is, if you have continuum radiation that is really escaping away from the region, then that can cause some of the emission lines to be weaker. So for any given ionization parameter and metallicity, what would happen is that if you're losing most of the Lyman continuum, then your C3 may not be as strong as you expected. So with increasing escape fraction, essentially your C3 emission will actually go down in strength. And this is one of the things that we're actually testing with an HST program that's currently on, using HST spectroscopy of green pea galaxies that are confirmed to be Lyman continuum leakers. So we can essentially test whether these, this relation with the escape fraction holds for the C3 equivalent widths, and look at the effect of escaping radiation on the nebular line strengths. So once we calibrate these, various diagnostics at low redshifts using the local galaxies, we then plan to apply these UV diagnostics to high redshift galaxies. And there are two approved programs that I'm already part of. One is the JWST GTO program, which is a Canadian nearest unbiased cluster survey. Nearest on JWST is the instrument that I work on. So that's why I'm part of the GTO team here. But the ERS program is a completely, it's a different science program, which was essentially, it was that was just proposal submitted by the community, and it was just open competition. So the early release program, both of these will be doing spectroscopy, and they will be getting UV emission lines. And I really look forward to actually using these data to understand more about reionization. So with that, I will stop. I think I've gone a little bit extra on time, so sorry about that. But thank you for your attention.
Thank you, Swara, for a very interesting talk and a very comprehensive overview of the UV-optical nebula diagnostics to probe the epoch of ionization. And thank you for a great presentation. So the floor is now open for discussion. And if anybody has any questions or comments, please unmute and speak.
Yeah, ma'am, may I ask a question?
Sure.
Okay, yeah, thanks for the nice talk. So the question I have, like, you showed one plot where you showed like the number of galaxies detected in the Lyman alpha emission as a function of redshift, and it shows like after z equals to 6, there is a drastic drop in the number.
Mhm.
So like, why that change is so drastic? Like, it's not smooth. Is it like the IgM opacity also increases drastically after that, or?
So that is an excellent question, and that really is what we are trying to figure out with. Let me just go back to the plot so that we have the context here. Um, okay, so this is the plot that you're talking about, right? So this drastic change. So this is with the current observations. So one thing we don't know is whether this is also the kind of you're really pushing HST to the limits, right? So there can be incompleteness in the sample. It could simply be that we have not detected.
Swara, the plot
I
is
think
not visible.
Yeah, the
The
slide is
slide
not.
that you are showing is not visible from here.
Oh, I'm
Yeah,
sorry.
yeah. Can you please
Yes,
check?
did I stop sharing? I did not. Okay, let me just do.
We're actually seeing the end of the slideshow, the last slide.
Do you see this?
Still not.
Not yet. You may have to, yeah.
You probably have to
Unshare
unshare and share again.
Yeah.
Yes. So this is the plot that you're talking about, right? Can you see it?
Yeah, I can see. Yeah, yeah.
Yes. Yeah. So this drop that you see here, these are actually the observed points as of now from HST, and we have actually pushed HST to the limit. But the thing to remember is when you go to in these deep surveys, the further and further you go, you're sampling the brighter galaxies much better than the fainter galaxies, right? The fainter galaxies are always difficult to observe. So you make some kind of a completeness correction. But the correction is again based on some assumptions that you say that if the galaxies are exponential disks, if the sizes of the galaxies are this, then this is the surface brightness that you should see. But if there is any other change, then it's all based on the assumptions that you make for the correction. So even if you correct, you may not really get the correct completeness correction. So we are hoping that JWST will actually show us these galaxies. You would be able to reach higher levels of completeness in the survey, and that should actually close the gap here. We hope so. I mean, but if you actually see a drastic drop, that would be very surprising.
Okay, so the opacity we cannot measure like beyond 6.
So yeah, so I mean, our uncertainty begins to increase as we look at higher redshifts, right? With the limits of the current data.
Okay. Okay. Thanks.
Yeah. And that is interesting what you're asking, because if that decline that you see in the UV continuum is really real, then it's really telling us something about the way galaxies form.
Right. Yeah.
I had a question, Swara.
Yeah.
You had that slide with the carbon 3 and the metallicity, the diagnostic diagram.
Mm.
There were some galaxies plotted in red.
Yeah, just a minute. Let me just get there. Sorry. Okay.
Yeah, this one. That's right. Yeah. So these points plotted in red,
Mhm.
okay, they kind of don't seem to be following the trend with other galaxies. So I was just wondering, are they a
Right.
particular type or what is the...
Right. So the thing is, most of these, so these red points are essentially the all of the UV spectra that was there for the solar metallicity and higher metallicity, like higher than 1/3 metallicity. So at higher metallicity, essentially, the problem is it's really difficult to get the carbon-3 lines because these are collisionally excited lines and you really need high electron temperatures. So what happens is when you look at the lower metallicity nebula, once you go to less than 1/3, right? So less than 1/3 would be around here, right? Because this is 1/5 solar. This is about 1/3 solar. That's the only time and these are my green pea galaxies that you see here in the green stars. So it's only once you go below about 1/3, what happens is, essentially you don't have coulants in the nebula anymore. I mean, the number of coulants is reducing. So essentially the electron temperature in the nebula is high. And then you can have these, very strong collisionally excited lines. And then you can see how it picks up with metallicity, right? If you just ignore these points, just ignore these red points here, and I'll tell you why. But if you just ignore them, then you can see that after 1/3, you have this nice relation with metallicity, right? I mean, lower the metallicity, stronger these lines. Now, these points, essentially, all of these four, these are not really four different galaxies. These are all Zwicky 18. So this is one Zwicky 18, and nobody really understands why. I mean, Zwicky 18, of course, has very low metallicity, but we don't know why these lines are, why the C3 is so weak. Now, one thing could be that by the time you go to these extremely low metallicities, first of all, the carbon abundance itself is low, right? That is one thing. And another possibility also is if you're beginning to get into the regime of very extreme ionization, some of the C3 would already be in C4 emission, right? They would have gone to a higher ionization state. So it could either be higher ionization has reduced that, or it could just be that the number of carbon atoms itself, the carbon abundance is so low. Yeah. So if you ignore these points, I mean, those are all actually different H2 regions within Zwicky 18. So if you ignore them, then you can actually see that the trend is pretty good.
Right. Okay. Oh, yeah. Thanks.
Swara, there is a comment in the YouTube channel. So Vageshwari, you remember? So she says,
Oh, yes, I do. Oh my God, of course.
so she says, thank you for remembering the library.
I do. I do. I remember the library, and I remember both Vageshwari and Christy. So some of the reasons, I mean, I actually, like when I was preparing this talk, I mean, everybody's face really started flashing in my mind, and the only reason I did not really kind of spell out people's names is because I was afraid that I would miss somebody's name, and I don't want that to look like I'm less thankful to them. I mean, it's just that there's yeah, it's almost like a family out there, right? I mean, I just remember everybody very well. I've spent enough years there, and I've had interactions with everyone. So, yeah, it's really like my family. So, I'm so happy she joined. I mean, Vageshwari, thank you so much for joining.
Thank you. So, are there any more questions or comments from the
Just a comment, Annapurni here. Nice talk, Swara. I think a lot of memories you also ignited in the audience. So, yeah, I think you put it across very nicely. Thanks.
Oh, thank you, sure. It was really heartfelt. I mean, I didn't have to try.
Hi, Swara. Sorry.
Oh, hi.
This is Ishwar.
Ishwar. Hi, Ishwar.
Sorry. So I had some other meeting. They had a serious problem with my computer connecting and things like that. So I couldn't hear your much of the talk. But now I could see you.
Okay. Thank you for joining.
Hi, Swara. This is Sujan here.
Hi, Sujan. Thanks for joining. Nice
excellent.
to hear you.
Yeah, nice to hear you. Last time I met you in Ayuka only. That's all.
Yeah.
It was an excellent talk. I had just one query that is not related to with your talk. I heard that this Hubble ultra deep survey that used infrared also. So, was there any great result? Means what type of science they did with the infrared?
So, I mean, if you're talking about the Hubble Space Telescope itself, then the infrared that you're talking about would be the near infrared. And all
yeah,
of
1 micron to 1.4 micron, if I remember properly. Yeah.
Yes, 1.6 micron. So all of the results that I showed you, basically, let me just quickly go back to. Um, Yeah, so all of these results that you see here, which is the, really the UV luminosity function from redshift 7 to 10, and also, all of these things that you're seeing, all of these points that you're seeing in this plot at redshifts greater than 7, those are all, completely the infrared data.
Oh,
Because the UV continuum would have redshifted all the way to beyond 1 micron, right? So all of that data essentially, yeah. So extending the cosmic star formation rate density all the way to redshift 10, that was completely from the near infrared data. And one thing I did not mention in my talk, which is also a significant component, is there was a GRISM survey, which is called the 3D HST survey program, which used the GRISM on HST to get near infrared spectra, very low resolution spectra, but still, near infrared spectra. And the highest redshift galaxy that we know now, I think it's at a redshift of 11, that essentially the spectroscopic redshift was confirmed by using the HST GRISM in the near infrared. So that was a big result. Yeah.
Uh-huh.
Hello, Swara. Thanks for a very fascinating talk. I had one question. There was an important statement. You said that BCGs are looking more like the green pea galaxies. Are you trying to say there is some evolutionary scenario between the two?
No, I really wasn't. So these different terms that we use, like blue compact dwarf galaxies or green pea galaxies, a lot of that actually has to do with the way these galaxies were selected. So blue compact dwarf galaxies are very local. Those are really pretty much redshift. If you looked at the redshift, it would be like 0.006 or 0.001 or something like that. So those are really, really local galaxies. So green pea galaxies, the only reason we call them green pea galaxies is because they have this very high oxygen emission, and that emission line falls in one of the broadbands in the SDSS filters. And when you kind of make these three color diagrams or three color composite images, are so green because the green color is given to the broadband filter, which essentially has the oxygen line. And because the oxygen line is really overwhelming the broadband emission, it appears in these, in the color composite images like these are green. So a better way of, so there is no evolutionary sequence. It's really just the names are given just based on the selection. And green pea galaxies are mostly in the redshift range 0.1 to 0.3. So a better way to understand all of these galaxies is just think of them as extreme emission line galaxies at different redshifts. So these are not really, and it's not really an evolutionary connection. Also think about the fact that the phase at which they are extreme emission line galaxies, that phase doesn't last across redshifts, right? Because it's a very short-lived phase. By the time you reach about 10 million years, that's starburst event has already died, and those stars have already exploded as supernovae. So it's just the way these galaxies are selected. It's really not an evolutionary connection from blue compact dwarf galaxies to green pea galaxies.
Thanks.
Okay.
Are there any more questions or comments? So if not, let's thank Swara again for a very nice talk. It's an excellent presentation. Yeah, and thank you all the participants for joining. I'll formally close this session.
And before you close, I just want to say, I mean, I know it's the holiday season, so happy holidays, and wish everybody at IIA a very happy New Year.
Happy New Year to you.
Thank you.
Same
Happy
to
New
you.
Year.
Thank you, Swara. Bye-bye. Stay
Bye.
safe.
You too.
Yeah.